the more we write these properties down, the better we'll be at them. So log base b of m times n, that's log base b of m plus log base b of n. We don't need to know the name of the property, just how to apply it. The second one, log base b of m minus log base b of n, because it was a division, so we turned division of two numbers inside of a single logarithm into subtraction of two separate logarithms. And the last one, the power property, we can move an exponent out in front. We did all of these things on the warm-up. All right, all three of them. Okay, now what we're going to be talking about today is how we can rewrite logarithmic expressions. We can either expand them or condense them. So expand or condense. And expanding is cool and all. I mean, you can do it. But condensing is really what we want to focus on. Condensing is going to help us solve equations. But if we're able to expand, then we should also be able to condense. So that's why we practice doing both. Okay, so start with this first one. Log base 6 of 5x cubed over y. So the first thing I want to ask you guys is, that 5 right there, is that 5 being cubed? Or is it only the x being cubed? Excuse me.
Just the x is being cubed.
Exactly, just the x is being cubed. That's really important to notice. A very common mistake I'll see from people on these types of problems is they'll put the 3 out front and then multiply by 5x, like that, but that is not accurate. Okay, just the x is being cubed. So we have to make sure that we follow an appropriate order so we don't mess up. Not the 5. All right, so what we want to do for this one, we'll start by saying let's do log base 6 of 5 plus log base 6 of x cubed minus log base 6 of y. I kind of broke it into 3 steps there. I'm saying we got multiplication on the top, those will add together. We have division on the bottom, that's going to subtract. Okay, now I have this 3 that I can move out in front. Log base 6 of 5 plus 3 times log base 6 of x minus log base 6 of y. All right, and that's it. That's our expansion right there. The big thing is just don't mess up on the cubed. Don't think that the 5's being cubed as well. That's a very common mistake I see. Another one I'll see is if we have two numbers being divided in the denominator, but they're being multiplied by each other in the denominator, we just have to be careful about whether we're adding or subtracting those numbers. And I'll show an example of that a little later. All right. Condensing means we're doing just the opposite. I have this log of 9 plus 3 times log of 2 minus log of 3. And whenever I'm condensing, I got to ask the same thing. Is the log of 9 being multiplied by 3 out in front of it? No, it's not. So what we want to do is we want to raise log of 2 to the 3rd power first. So we can rewrite this first as log of 9 plus log of 2 to the 3rd power minus log of 3. All right. And now we can go ahead and condense this thing. We can go ahead and say log of 9 times 2 to the 3rd divided by 3. That's when we rewrite it as a single logarithm. And we can actually do even a little better than just that, because we have 9 times 2 to the 3rd divided by 3. We can actually simplify that. 2 to the 3rd is 8. So we get 9 times 8 divided by 3. And then 9 times 8 is 72. 72 divided by 3 is 24. So this simplifies all the way to log of 24. Okay, that's the idea here for these particular problems. So work on the steps and simplify as you go. That might make it, you could simplify as you go. That might make it a little easier. Like you could cube the 2 before you combine it and just say, then you have 9 times 8, and then you get 72, and then divide that by 3, and you get 24. That might be the easiest way to approach it. All right, but a couple different ways to look at it. All right, your guys' turn. I have 2 examples here. Log of 3x to the 4th, expand that one, and then condense the other one. 3 times natural log of 4 minus natural log of 8 plus natural log of 5. All right, good luck. So we can go ahead and look at these 2 problems. Expand log 3x to the 4th. So the big thing with these expansion problems is it's almost like working backwards, because typically when we do PEMDAS, when we're solving, we want to do exponents first before we do multiplication. But with these expansion problems, since that 3 is not being raised to the 4th power, we really want to separate these 2 first. So log of 3 plus log of x to the 4th. And then after they're separated, we can pull that 4 out in front. All right. A good way to double check is to always think about, if I were to put it back together, would it look the exact same? Like if I had a 4 in front of the log of 3, then that would be 3 to the 4th, that would make it 81, and that would not be the same. So that's one way to kind of think about it when you're trying to put it back together. For problem 2, I have this 3 natural log of 4. So I'm going to rewrite that as natural log of 4 to the 3rd power. And then again, I can just go ahead and simplify that right now. 4 to the 3rd power is going to be 64. And now I'll just work from left to right. So I can rewrite this as 64 divided by 8. Well, 64 divided by 8 is just going to be 8. That simplifies nicely. Oops, and then that's plus, sorry. And then I have natural log of 8 plus natural log of 5. So that's going to be natural log of 8 times 5, which is natural log of 40. That's what this one would simplify to when it's all condensed, which, in my opinion, I think that looks a whole lot easier to deal with than 3 times natural log of 4 minus natural log of 8 plus natural log of 5. So that's the idea with condensing, is that we're going to hopefully make these problems simpler. And when we're solving, condensing is a really useful method to help make things a little simpler to work with. Any questions on 1 and 2 before we move on? All right. So the property of equality for logarithmic equations says if b, x, and y are positive numbers with b not equal to 1, then log base b of x is equal to log base b of y if and only if x equals y. So pretty simple statement there. It's just saying if you have 2 statements that are equal to each other, 2 logarithms that are equal to each other, then the statements are also equal to each other. So we have log base 2 of x equals log base 2 of 7, then x equals 7. All right, because the 2 statements have to be equal. So similarly, if x equals 7, then log base 2 of x equals log base 2 of 7. It goes both directions there. You can do that either way. On your homework yesterday, problems 9 through 14 had some weird logarithmic functions. If you left the Zoom call early, I said we can throw those problems out. We don't need to worry about them. So if you didn't finish those ones, that's fine. Those ones were, those ones are tricky. Yeah, so that's 9 through 14. I just crossed them out, so don't worry about those problems on the assignment yesterday because we hadn't done an example like that yet. We're going to do those examples today. I kind of jumped the gun on putting those on the assignment. Sorry about that. Okay, so example 5 is kind of what I was talking about with this property equality of logarithmic equations. We have 2 logs. Both of them are log base 5. And they're equal to each other. So that this rule up above says then therefore the equations should just be equal to each other. We can get rid of those log base 5s. That's kind of nice. So now we've got 4x minus 7 equals x plus 5. And I can just solve algebraically. Let's subtract x from both sides. So 3x minus 7 equals 5. Let's add 7 to both sides. 3x equals 12. And then divide both sides by 3, and we're going to get x equals 4. All right, that's the idea here. Once we get our answer, we're going to need to check it. Go back to the very beginning, and we'll just say log base 5 of 4 times 4 minus 7 equals log base 5 of 4 plus 5. And we should hopefully get something that's like log base 5 of 9 equals log base 5 of 9. That's kind of what I'm seeing here, because I have log base 5 of 9 on the right side. And sure enough, I get log base 5 of 9 equals log base 5 of 9. Put those into your calculator, it checks out. Perfect. The only thing I don't ever want to see inside of a logarithm is a negative number. And in this case, it looks fine. So if I got something like log base 5 of negative 9 equals log base 5 of 9, that would be a problem. But that's not the situation here. It looks like it worked out. So x equals 4 is indeed a solution. We can go ahead and box it up. All right, that's what I have in the notes here, is check for extraneous solutions. And what it is when we solve it algebraically, we get a solution, but then it turns out that solution's not really an answer. So that could happen from time to time, and that's what an extraneous solution is. That's why we have to double check our answers, especially with these logarithmic functions. We're doing two things. We're verifying that we solved the problem correctly, and then we're also proving that, hey, this answer is an extraneous solution. It's not a real solution for this equation. It won't work. All right, here's another one. Log base 4 of 5x minus 1 equals 3. So when we do this problem, we can do it two ways. We have this log base 4 here. So the first one we can do is change forms. It's all the logarithm's isolated on one side of the equation. So I can say this is solving for the exponent. The exponent's 3. So I could technically say 4 to the third equals 5x minus 1. That's changing forms. 4 to the third equals 64. I'm going to add 1 to both sides. 65 equals 5x. Divide both sides by 5, and I get x equals 13. That's one method. So if you like changing forms and that's easy for you, great. All right, do that. If you don't like changing forms, there's another method we could technically use here. Yeah, let's do this simply. And this is what method 2 would look like. So the second method would be, if I see a log base 4. So technically, whatever I do to the left side of the equation, I can do to the right side of the equation. I'm going to take base 4 to both sides of the equation. That keeps the equation balanced. That's what I talked about yesterday. You always want to keep the equation balanced. And I specifically chose base 4 because there's a base 4 in the logarithm. And what technically happens is I have this log base 4 of 4. That's almost like a logarithmic property of exponents, where the 5x minus 1 can move out front, and the log base 4 of 4 becomes a 1. So I would end up with 5x minus 1 equals 4 to the third. So I get to the exact same step I got to on method 1. But if for some reason that change forms doesn't make sense to me, I'm not very good at it, whatever, and I'm more of an algebraic thinker, I like to do operations to keep equations balanced, then you can do this method instead. Either one of them is perfectly fine. All right? And personally, for me, I think it's easier for me to see it rather than memorize this change forms thing. It's easier for me to see, oh, I can just do base 4 on both sides, and now I've got 4 to the third power, and this thing's not screwed up. And then we would end up solving this again the exact same way, and we get x equals 13. Okay. Once we get that answer, we're going to check log base 4 of 5 times 13 minus 1 equals 3. And when we're double checking our answer, one thing we might notice is we'll see a lot of the same numbers. So for example, 5 times 13, I see 5 and 13 over here. It's like undoing these steps. And then minus 1, there it is. 64, there's a 64 over there. It's kind of weird. And then it turns out log base 4 of 64, that is actually 3. So this just becomes 3 equals 3. And it checks out. So x does equal 13 is a real answer to this equation. All right, so that was 2 methods for solving the exact same problem. All right, but we have to make sure that logarithm is isolated before we do anything else. Okay. Any questions on those first 2 problems before we move on to the tough one? All right. So let's take a look at the last one here. It says solve log of 2x plus log of quantity x minus 5. Now this one, let's see, I'll do this right here. I cannot change forms, so I can't change forms unless there is a single logarithm on one side. On one side of the equation. And right now, there's not a single logarithm on one side. There are 2 logarithms on one side. So what can I do to get 2 logarithms and turn them into 1 logarithm? This is where that condensing comes into play. I have 2x, log of 2x, plus log of x minus 5. So I can rewrite this as a single logarithm multiplied. And then I can go ahead and distribute this 2x minus 5. And I get log of 2x squared minus 10x. And that all equals 2. Now I need to change forms. All right. So I can either do method 1 or method 2 from above. Anyone know what the base of this logarithm is if it's not written down?
10.
Yep, exactly. It's going to be base 10. So I'm going to do method 2 here. Just show you guys that one more time. I can do base 10 of both sides. And on this left side, because I have 10 and log base 10, it's just going to be left over 2x squared minus 10x. On the other side, 10 squared is 100. So now this gives me horrible, horrible flashbacks of AGS2 from last year. I've got myself a quadratic equation, and I have to solve a quadratic equation to solve this problem. So I have to subtract 100 from both sides. 2x squared minus 10x minus 100. And then from there, I want to simplify this. So I want to be able to break it into 2 binomials. That's what is good about quadratic equations. Right now I see a 2, a 10, and a 100. So actually one thing that could make this a lot easier is let's divide everything by 2, both sides of the equation by 2. The nice thing, because 0 divided by 2 is just 0, but 2 divided by 2 is 1, 10 divided by 2 is 5. 100 divided by 2 is 50. That's going to make this a lot easier to deal with if I divide by 2 like that. And now I have to think about what factors, hopefully I can factor this, what multiplies to get us 50 and adds to get us -5. So think about factors of 50, like 1 and 50. Those multiply to get 50, but if you subtract them, they're 49. 2 and 25, that gives us 23 if we add them. Okay, so you just kind of work through it like that. 3 doesn't work, 4 doesn't work, 5. 5 times 10. And 10 minus 5 is -5, so that would work. So it's got to be like a 10 and a 5 in here. And I want a -5, so I'm going to need the bigger number to be negative. All right, so I did that really fast in my head. If you need to, you can do the factor box method that we did last year, where we put x squared minus 5x minus 50 in there. And we just kind of mess around with it and say, okay, well, I have to do like a -10 and a +5. And that's going to get me a -10x and a +5x. And those add together to get me that -5x in the middle. So that's where my x plus 5 and my x minus 10 come from. So you might have to play around with factor boxes. That might help you figure out how to factor this particular problem. All right, but those ones are very tricky. This is just bringing flashbacks of AGS2, I hope. You remember this from the fall last year. Now, x minus 10 and x plus 5, we can rewrite that as two separate equations. There's that thing called the zero product property. If two numbers multiplied together equal 0, that means one of the numbers must equal 0, but we're not sure which one. So we say x minus 10 is one of those numbers, that could equal 0. X plus 5 is the other one of those numbers, that could equal 0. And we solve for each one individually. Add 10 to both sides on this one, you get x equals 10. Subtract 5 from both sides on this one, you get x equals -5. Two possible answers. All right, now the last part is we got our answers. Let's check them. Check. Do you want to check 10 first or -5 first? Doesn't really matter. Let's start with checking 10. Plus log base 10 minus 5 equals 2. So we end up getting log of 20 plus log of 5 equals 2. Log of 20 times 5 equals 2. 20 times 5 is 100. And then we have log base 10 of 100, which indeed does equal 2. So that's perfect. That one checks out. 10 is an answer. Let's check -5, the other one. I'll do this one in yellow. Log base 2 of 2 times -5 plus log base 2 of -5 minus 5 more equals 2. And I end up getting log base 2 of -10 plus log base 2 of -10. Okay, and right now I have a problem. There's something I never want to see inside of a logarithm, and I'm seeing it twice. I never want to see a negative number inside a logarithm. Negative numbers are bad in logarithms. They give you an error message on your calculator. If you try to take any log with a negative number, it's going to give you an error message. So right now I can tell you this one's not going to work.
Do you flip it?
What'd you say?
Do you flip it?
No, you don't flip it. That would be if there was an exponent, if it was a negative exponent. On this one, it's just not going to work. So we would say, we would cross that one off, and then I'm just going to make a little note. Like, I found this solution, but this one happens to be extraneous. So I'm just going to write that down. Extraneous solution. Not going to work for me. Okay, so that one's a really tough problem, that third one. Okay, there's going to be one similar to that, I think, down here on the your turn part. I want you guys to try those next 4 problems. I'm going to give you about 10 minutes on these. They take a while. All right, but take your time. If you have questions, feel free to ask me. I'm going to set a timer. All right. Timer starting. Good. Okay, so for these 4 problems then, I'm just going to put the answers down. The first one should have gotten x equals 3. Okay. Second one, we should have had something like x equals 38. The third one, we would have had 2 answers, x equals 5, x equals -4. But this one was an extraneous solution, so I'm going to make a note of that. And then the last one, I would have had like an x equals 4 and an x equals -16. And again, when I plugged this one back in, it was another extraneous solution, so I'm just going to cross that one out. So you have one solution for each of these 4 problems. Are there any that we want to see worked out? Let's see. So number 4, we'll take a look at number 4. Any others? Okay, so we'll start with number 4. This one has log base 4 of x plus 12 plus log base 4 of x. So first thing we're going to do is we're going to combine them. X times x plus 12 equals 3, so a single logarithm, and distribute that x. So it's log base 4 of x squared plus 12x equals 3. And now we can either change forms or do base 4 to both sides. And we're going to get something that looks like this. X squared plus 12x equals 4 to the 3rd power. And 4 to the 3rd power is 64. And then I subtract 64 from both sides. And I get x squared minus 12x minus 64. I'll write it a little bigger. Equals 0. And now I'm trying to factor it. So I might need to use a factor box method, something like that. So like factors of 64, 1 and 64, 2 and 32. 2 and 32 won't add or won't subtract to get us 12. 3 doesn't go into
positive 12?
What'd you say?
Positive 12?
It is positive 12. Sorry about that. Good catch. Anyway, so then I would try something like, let's see, I could try 4 and 16, something like that. So I mean, trying to figure it out. And I think this one, it did come out to 4 and 16. And what happens is if we do a positive 16 and a negative 4, that's going to get us a positive 12 over here. And when we set these up over here, we get an x plus 4 equals 0, or an x minus 4 equals 0, and an x plus 16 equals 0. So we get an x equals 4 and an x equals negative 16. And that brings us to the check. And I already know the x equals 4 is going to work, so I'm just going to check the other one for you guys right now, just to show you what an extraneous solution looks like again. So we do log base 4 of negative 16 plus 12 plus log base 4 of negative 16 equals 3. And again, all I'm looking for is when I put the negative 16 in, I'm going to have a negative number inside of a logarithm. The other one, I do need to simplify it first. It is possible to plug in a negative number and then it adds up to a positive number, but in this case it doesn't. I get a log base 4 of negative 4. So that's how I know this is going to be an extraneous solution. Okay, but the other one should work when we plug it in. Okay. So that's problem 4. That one's the tricky one. Those ones are tough. And on your next assessment, you're probably going to have one at that level. That'll be like that'll be one of the hardest problems on the test is can you deal with these quadratics, bringing stuff back from AGS2. Okay, but we should be able to solve these equations. That's going to be something that will be on the next test. So we're going to practice on that in the assignment tonight. And I'm not sure when the next test will be yet. I think it's going to be not next week, but the week after, I think, if I remember correctly. Anyway, I will keep you posted on that. All right, the last part, solving exponential and logarithmic equations by graphing. So you can solve any equation using a graphing or utility calculator. You will be required to use algebraic methods on your test, but this is a handy way to check your answers or to solve more complicated problems on other exams like the ACT. So it's really useful for the ACT because that's a timed test. But how do I solve these by graphing? So if this first equation is something you have, yes, I can condense them, I can distribute, I can solve this crazy quadratic equation. To use the graphing method, the first thing we're going to do is write two separate equations. Two y equals equations. So we can say y equals log of 2x plus log of x minus 5, and y equals 2. And now I can put those in my calculator. Two separate y equals equations, I can put them on the graphing calculator. And then I'm going to find the intersection of the two lines. So not everyone in here has a graphing calculator, I'm guessing, and that's fine. But if you do have a graphing calculator, it is very useful on a test like the ACT that you guys would be taking this year as juniors, maybe even sophomores. But if you find the intersection of the two lines, that would be our solution for x. All right. So I'm not going to show you, like I said, the exact demonstration today. But if you type it in on the y equals sign and you graph the two lines, you'll see an intersection point. And you find that intersection point, and that's your solution. And it turns out for this one, I think it was like x equals 10 or something like that. All right. Another crazy difficult example is this like log base 5 of 5x minus 1 equals log base 8 of 3x. So if you have a calculator that allows you to put those straight into your graph, into your calculator as two y equals equations, you can do that. Otherwise, you might need to change the base first. And that's going to make this look like a really ugly equation. But you can say, let's do log of 5x minus 1 divided by log of 5. That's one equation that equals y. And the other one's log of 3x divided by log of 8. That's another equation that equals y. And you do the same thing, find the intersection of the two equations, and that's your solution. All right, that was a lot. Okay, but that's the idea for solving exponential and logarithmic equations. And that's how we could do this on the ACT and do it a lot faster. All right, but on our first test, we'll probably be asked, can you show me algebraically how to do it? Or on our next test, I should say. All right, your assignment tonight, problems 1 through 4, expand, problems 5 through 8, condense, and then the last few problems, 9 through 14, this time they're in the right spot. Check for extraneous solutions on the logarithmic ones. So you don't need to check for extraneous on 9 or 10. It's always good to double check your answers though. But on 11, 12, 13, and 14, you'll want to check for extraneous solutions. Extraneous solutions, again, those exist. Think about our domain. If our domain has x values where it's like 0 to infinity, and we have a number that's a negative number, then that's why it's outside of the domain. So it really depends on where the domain falls. That's another way you can test to see if something's extraneous. And we can take a look at that on Monday, something like that.